Hey guys, this is an updated video for the Spearman's correlation for your paper 2 test tomorrow, and this is covering section 4.4 for population sampling. So I'm gonna go through the document that I have made that covers it just step by step, and then I'm gonna do an example exam question. This is from the May-June 2022 paper 2 version 2. Okay, so the purpose of using a Spearman's rank correlation is to see if there is a correlation between two sets of numbers that maybe aren't distributed normally. So not distributed normally, it's a mathematical tool or statistical tool to find out if there's a correlation between two sets of variables, two sets of numbers, or two factors. Okay, so just because things look like they might correlate doesn't mean they're the cause of each other, and this will help determine that. I'll show you an example of what I mean by they're not distributed normally. So this is a data set that we're going to work with that I made. And if you look like species A cover, it goes 0, 1, 2, 10, 8, 9, 11, 7, 4, 3. Likewise with B, 0, 5, 14, 25, 28, 30, 40, 32, 28. So there isn't any specific correlation between them. And not necessarily that, I'm sorry, that there's not like as an obvious increase in those values, and then it's causing an increase or a decrease in the other factor, the other value. We're not seeing species A cover go from 0, 1, 2, and then a numerical order. And if that was the case, then we could say a species A cover increases and species B cover, and then whatever species B does. But we don't see it like that. So instead, we're going to have to rank them to identify if they have any sort of correlation together. So when you see this on an exam, you may or may not, I mean, you won't, honestly, you won't have to do the entire steps. You might have to do some parts of the step. For example, in the paper 2 that I'm using, and this is from May, June 2022, this is paper 2, version 2, they do the entirety of this for you. You're just going to have to then do the sum of d squared, identify what your n value is, and then plug it into the formula. So this one, despite it looking so nasty with its alphabet in there and the Greek alphabet, English alphabet, Greek alphabet, and then of course there's so many parentheses and words of operations, it's actually not that bad. All right, so if you need to, or it might be done for you like you have in the exam question, you're gonna have to do a scatter plot with the data once it's gathered. And this is just to identify if there is any potential correlation. So if you have in your x-axis, if it's increasing and that's you see an increase in the y, that's a positive correlation. If your x-axis is increasing and it's causing the y to decrease, maybe like as depth increases, temperature decreases, that would be a negative correlation. Or if when you put the line of best fit or your trend line, there's none, then there is no correlation. However, you're not going to end up in a scenario where there's no correlation or they wouldn't test you on it. If you realize there's a correlation, then you got to do some math to see if they're like how probable is that correlation. What's like your confidence, how there it is, like how confident you are in that correlation. And there's a value that we're gonna have to look at so we can determine it. And so in the example that I prepared, we're gonna use like a quadrat, a framed quadrat on a rocky shore. We have 10 random samples that were taken. All right, so I'm using a framed quadrat, something like this, with the lines in between. And that way we can identify like species coverage. So how much a species covers. And this is again to measure the abundance of two species, A and B. Data for the percent abundance was recorded using the AICE scale. And other than just me mentioning it there, we're really not going to use it anymore in this scenario, but it is something that is mentioned within the limits of the syllabus. And this just shows if in that quadrat you have 90 to 100% coverage, and that's in this table example, we would say that species is abundant, 50 to 90, common, etc., etc. And that's why it's called AICE. Okay, and so the data collected for both species is, and you have it right here, The way that this is ranked is based off the quadrat sample. So sample 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then you recorded the abundance for each species. Okay. The exam question I have does not ask you what is the null hypothesis or to create one, but you could. So essentially, a null hypothesis will always state that there is no correlation between the two values. And I've always thought that this was like unnecessary. It's just like saying the opposite of your hypothesis. That's just my personal thought on it. Just always thought that. So a null hypothesis. A null would mean like void or not. It's like the not hypothesis. If we think the hypothesis is that, look at this graph that I made, and this graph is made from the data table. That if you look here, the trend line that was put in. So essentially it's saying that as species A percent cover, as it starts to increase, 2, 4, 6, 8, 10, then likewise species B cover also increases. So it does look like there may be a positive correlation. We won't know. And so if our hypothesis is that species A cover, if it increases, then species B cover will increase, or vice versa, or that species A cover controls species B cover. The null hypothesis would be this, and this is essentially like a sentence stem that you could use anytime that you're having to state the null hypothesis. There is no correlation, and if you don't have, for my students in class, if you don't have this printed on there, because I did update it with that in classes today, we did write that in the area, in this area, then you can just put null hypothesis and then write this. There's no correlation between the percent cover of species A and species B. Honestly, you're gonna get a different scenario perhaps, and in that you're gonna say there is no correlation between insert whatever they're giving you as like their factor or whatever they were measuring. Insert the second thing. That's it. So the sentence will stay the same. You're just gonna put in different variables or different measurements. Okay, so the scatter plot is made. Scatter plot is going to be made just like a line graph, except you're not going to connect each line to each other. Instead, you're just going to see where there is like a line of best fit. You're not going to do that. All right, I already highlighted the main things for you. So the next step, we're going to rank each data set for species A, or whatever data set or factor that you have, whatever measurement you have. And we're going to start with the highest percent cover. The highest data point, or for that, the highest percent cover, or whatever your highest data point is, you're going to give it a ranking of 1. And in this scenario, quadrat 7 having 11%, that is going to be your ranking of 1. And this is for species A. So here I have my quadrats labeled. And so at quadrat 7, it being 11%, and if you look, that is the highest value percent covered, that's going to be a 1. The second highest after that is going to become the ranking of 2. And as we do this, you'll see that we are going to have numbers 1 through 10, because there's 10 quadrats, and we're just going to list their rank. Here we go. We're also going to do the same for species B. So we're going to do this for all of the species A data sets, and then we're going to do it for species B. Species B, 40 is going to be your biggest one. That's my 1. And if anybody wants this document, I should have said in the beginning, on my Teachers Pay Teachers account. So teacherspayteachers.com, you can search my name, or I think the store is called AICE Marine Depot, because of course it is, Depot. This is on there, and it's Spearman's rank correlation, and then you can purchase it and you can own it forever. Give it to all your friends. 2 is going to be the 32, 3, and then just keep on filling in for the ranking. Okay. Something to consider, if there's a tie in the ranking, or if you have, like for mine, percent cover, and if you have 2 of the same values, for example, in species B, if you had like one was 10% and another one was 10%, you're going to add up both of those ranking values and then divide by 2, and you're going to give them the average of the ranking values. You're not adding up the data, because that wouldn't make sense. If you said 10 plus 10 divided by 2, obviously it's going to be 10. It's the average value of the rankings that they should be. So for example, if you were starting and you already had numbers ranked 1 and 2, and then you got to the 10, and so the next number should be 3 and then 4 in your ranking, but they're both 10, so how do you know which one is which? You're going to take these 2 numbers, add them together, and then divide by 2 to get the average. There you go. So you're going to split in half. So nobody gets to be ranking number 3. They both get to be 3.5. Now you're not going to, I don't know that if you would have to do that. I feel like it would be kind of like a very specific detail, but you will see in the exam paper that I have, you do have things that had to split the ranking. Here in the rank, you see it 8.5, 10.5, 8.5, 10.5. So they have had to split their ranking. And you can get this exam paper from just Googling May, June, paper 22, 2022. You probably want to include the syllabus code 9693, or you can type in marine science 22, May, June, 2022. And then you can just download those pages. These pages are 15 through 19. And they're listed at the top, 15 through 19. You could also download it if you have an iPad or something electronic like that too, so you can also do this if you don't have a printer. Okay, so that's the next step. So far all we've done is said, hey, it looks like there's a correlation between the data, and then we ranked the data in order from largest to smallest, starting with the number 1 and ranking them all the way up to 10, or however many samples that you have. Next, we're going to calculate the difference in the rank. So that's going to be subtraction. And that is going to be what, I was going to say what the D stands for, but the D is the difference in the species ranking. Or the difference in ranking, not species ranking, because it could be anything they're measuring. Difference in the ranking. On here, I just want to just draw some attention to this. It says the subtraction order doesn't matter. You want essentially the absolute value, because I do say subtract species B from species A. And even down here in the corner, species B rank minus species A, and I color-coded them for you. Truthfully, it doesn't matter. It doesn't matter, because if you recognize the formula, when you get to what D is, you're going to square it. So even if you subtract wrong, or you subtract backwards, and you do 3 minus 1, which is 2, instead of 1 minus 3, which would be then a negative 2, it won't matter, because when you square that, you're going to get a positive value anyways. So it's not gonna make any difference. So there's nothing to worry about if you think that you're subtracting it backwards. All right, and so I did color code it for you. So 10 minus 10, that's 0. 9 minus 9, 0. 8 minus 7, or 7 minus 8, it doesn't matter. This is going to be the 1, and for the sake of just following my pattern, I'll do it because I know I have it on the next page. So 7 minus 8 would be a -1, but it really won't matter. 5 minus 2, it's going to be 3, negative. Never mind. 0, 0, 1, 2 minus 5, -3, 6 minus 6, 0, and then 8 minus 7 is going to be 1. Sometimes the hardest thing is just subtraction. All right, but again, the negatives don't matter. It won't matter, and you'll see in just a moment why. All right, the next thing. So step 4, for each value of D, for each value of the difference in the ranking, difference between species B rank and species A rank, square the value. All right, so now we just did this one. We're going to square it. 0 squared is 0. 0 squared is 0. -1 squared is 1. And this is why I said it won't matter if you put a positive or a negative. Essentially, you're going to have the absolute value. 3 squared is 9. 0 squared is 0. And we're doing this. And that's this part of the equation right here. Just the D. 0 squared, 0, 0. -3 squared is 9, 0, and then 1 squared is 1. All right, if you do have the paper from class, you are going to see an error, and it's right here, and Xavier from 4th period pointed it out because, again, copying and subtraction, just sometimes I'm a poor soul. Your paper has a number 1 right here, and that shouldn't be. And I did edit this to now make it a bit more correct, but that shouldn't have a number 1 there, which is actually going to cause issues for this area. So just keep out for that. And in most classes, I was able to show that that was what was going on. Well, I guess not first or second because Xavier's in 4th and that's when he caught it. Anyway, we're going to do the summation now. The summation, that's what your sigma is. It's a glorified plus sign. So add up to find the sum of D squared, D squared. 0, 0, 1, 9, so there's 10, 0, 0, 0, 19, 0, 1 is 20. All right, so I think the scariest part of this formula you just did, you just solved for the summation of D squared. So this part is done. So we're going to have 6 times that number, 20, and then we need to identify what n is. N in this formula is not the same as n in the formula for Simpson's index of biodiversity. Also, the D variable is not the same in both these formulas, and that really isn't anything to worry about because you never have to memorize them, nor do you have to memorize what their variables are. They'll be given to you. So now we can substitute in the values for Spearman's rank formula, and we're going to find the critical value. That's just what it's called. We just calculated the sum for D squared. Now we need to identify what n is. N is going to stand for number, the number. Similar, though, it also stood for a certain number in Simpson's index of biodiversity. And in this one is the number or the amount of pairs of items in the sample. We did 10 pairs of items. And what those pairs are, what they look like, is essentially like how many times you took a sample of something. How many data sets that you have. That's the pair. So here's a pair, here's a pair, here's a pair, here's a pair, here's a pair. The number of pairs is like textbook talk, but the reality is it's going to be the amount of data sets that you have. And I did the quadrat 10 times, so I have 10 data sets, and it's a pair because you have 2 things, you have species A and species B. And that is what your value for n is. N won't be given to you in an exam. They'll tell you what it means, but you're going to have to be able to figure out from looking at the data, like how many data sets did they take. Okay, And I have some space over here, so I'm just going to put that. N equals 10. And you do need to have n cubed. So it's going to be 10 cubed. So 10 times 10 times 10, 1,000. All right, and so I did substitute in these values for you. So we have 6 times the summation of d squared, which we just found out right here, it's 20. So 6 times 20. And then you're dividing it by n cubed, 1,000, minus n, which is just 10, your number of data sets that you have. So if you multiply them, 6 times 2 is 12, add your 0, 120, and then divide it by 990. All right, and I left that blank for you guys to fill in. Okay, if you divide that, you're going to get 1 minus 0.12. And again, in class, if you got this in the morning, or even, no, and even, not even this morning, sorry, everybody who got it yesterday, shoot, you probably have 21 here, which that's not correct. And that's not going to have the same values that I do. And I think this one was 126. All right, so 1 minus 1.2, and that's going to equal 0.878. So your RS value is 0.878, and that's the ranking. The little S is for Spearman, and the R is for ranking. Or you can put, 0.88. Now, a couple things to consider. An easy way to look at this and be like, so what does that number mean? If it's closer to 1 than it is to 0, then it has a pretty strong correlation. It has, and this specifically is a strong positive correlation. Now, if it's closer to like 0.5, that's a very weak correlation. Well, I guess it's not very weak, but it is rather weak. Like you're going to see that like 0.6s are not so strong. But if it's closer towards 1, then that's going to be a pretty strong correlation that the percent cover of A does correlate with the percent cover of B. They do have that in common. Or that's an easy way to do it, and that's actually what's going to be on the exam question that we're going to do, but that might not always be the case. Or we can use a table that already has expected critical values and compare what the critical value is from the table with what we just calculated. And so that situation will be step 7. So to test if the calculated value for Spearman's rank is significant, we will have to compare it to a table with critical values of our little s, which is Spearman's ranking. This will always be given to you, this table, if they want you to use it. Otherwise, and like you'll see in the exam question, we don't use a table. We have to make an inference about the value of 0.88 or whatever value that you calculate. So this is called a p-value, and if you've had statistics, then you probably have seen it. So a p-value, and I just did a portion of this table. I just screenshotted a portion of it. A p-value will tell you how much confidence that we have that these data values actually do correlate together. And in this class, we will always use a p-value of 0.05. That is a very common p-value to use, or 5%. And so essentially this means that we have 95% confidence. There's 90% confidence that the values do correlate with each other. Or we can say with a 95% confidence interval that the percent cover for species A and species B do correlate together. On the flip side, there's a 5% chance that they do not. So we have a very good chance that they do correlate. And so to find what our p-value actually is, we need to identify, again, what our n is. And in this case, the number of data sets we have are 10. So N is in the left column of the chart. Here's N. And we're going to look for the amount of sample pairs that were taken. And we had 10 pairs of quadrat samples. So we're going to identify 10. Obviously, because I already did it for you. And then the critical value for the Spearman's rank at 0.05 probability or 0.05 confidence interval is going to be 0.648, or we can round that to 0.65. All right, and then again, this table will always be given to you. Nobody ever, never, ever memorizes this. There's no way. So for an N value of 10 and a confidence interval that there's only 5% chance that these don't correlate, the critical value that we should be comparing to is 0.648. And this value here, that 0.648, that is more of like a comparison. So you actually have a standardized variable, that value that you can compare your calculated answer to. And that's the next thing, comparing our calculated critical value, and that's from your formula, with the critical value from the chart. And so the critical value that we calculated is 0.878 or 0.88. And this actually needs to be corrected. That value should be 0.88 if you're rounding up. And again, that's because I did an extra 1 at the top. All right, because our calculated critical value for the Spearman's rank was 0.88, we did that out of the formula. Because it's greater than 0.65, we will conclude that there is a correlation between species A abundance and species B abundance. And we can say this, because we used a p-value of 0.05, we can say this with 95% certainty, or only 5% uncertainty, which is, statistically, that's a really good value. AKA, the numbers are the cause of their correlation, and their values are not coincidental. So it's not just random that when species percent cover A starts to increase, that it also happens to B. It's not random, they do correlate. They're not accidental. They do relate to each other. And then bringing us back to our null hypothesis, the null or void or the not hypothesis, if you are asked to create a null hypothesis or ask if you, and this is always weird that they talk backwards like this, but if you accept or reject the null hypothesis. Again, our null hypothesis said that there's no correlation between them. So if we accept the null hypothesis, that means that we accept the statement that there actually is no correlation between them. We're not going to do that because our calculated value for the ranking of those data sets was 0.88. And that's greater than the p-value that's given on the chart of 0.65. So we will say that we will reject the null hypothesis, which I realize sounds like you're talking in double negatives. I will reject the void hypothesis. And I don't know why one can't just say, we accept our hypothesis, like just the OG, the original one. Statistics always has like a null hypothesis. I didn't make it up. So the null hypothesis is, it always states that, again, there is no correlation between your samples. And so because of our data, because our calculated critical value is greater than the one on the table, we reject the null hypothesis that there is no correlation between species A abundance and species B abundance. And that it's if they ask you about the null hypothesis. Finally, we will accept the alternative hypothesis, which is probably your original hypothesis, that there is a correlation between species A and species B abundance. Okay, so that's just the step-by-step of doing all of it, and you might not have to do all of it. All right, so on a rocky shore, Parma victoriae is a common species of fish living on rocky reefs. And if you would like to see it, looks like this. So different versions of them. Notice the species name. You have the genus capitalized and the species name is lowercase. You can identify that it is a species name because it is in italics, but when you write it, you're going to capitalize the genus and lowercase the species. Okay, species of fish living on rocky reefs. They're highly territorial. They aggressively defend their territory from other fish. Scientists investigated the factors affecting the amount of aggressive attacks by P. victoriae. In the table, you see the number of aggressive encounters, and that's right here, the amount of aggressive encounters with various types of other fish. And your various types of other fish, I'll just identify that, with various types of other fish. Population density, so the amount per area, population, the amount of a species, and then density, like the area that it's in. Density is mass over volume, so essentially the mass here is the population number, and then the volume is the space that they're in. And so the population density of species is going to be their average number per 500 square meters. So for example, this Saceperca wrasser, this first one, there's 84 of them in 500 square meters. All right, additionally, and this might be data that we'll need to use later, and it is, we see the food source and the population density of each species. And so we have their species, the amount that's in their population, the food source for them, and then the number of aggressive encounters specifically with the P. victoriae. All right, first question. Use the table, state the number, so you're going to need to say a number of aggressive attacks or aggressive encounters due to intraspecific competition. Now, you guys were already tested on this on Monday if you were a part of the paper 1 version 1 group. And then explain or give reasons for your answer, so why you chose that one. It's 2 marks. 1 mark is going to be the number that you give, and the second mark is going to be your rationale. So P. victoriae is the species name, and if there is intraspecific competition, that means that it's competition between your own species group or the same species. So in the chart, we want to look to see the P. victoriae or Parma victoriae, and there it is. And then the number of aggressive encounters is 61. And so it's going to be 61 aggressive encounters. And then what was our rationale for that? So the reason is because this means that there's competition between the same species, and same needs to be there. Okay. Just for practice, because they are going to give it to you in this question, but just for practice, I'm going to do the rankings of them. They do give it to you, but again, practice. Okay, so the amount of different samples that you have, first of all, we can identify what N is right away. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. So like I said before, this example has 11. And so the data that they actually got was what is the population density, so how many per that area, and then the aggressive encounters. So there's and these are the pairs, right? This is a pair of data, this is a pair of data, this is a pair of data. So n is 11. We're going to need that later. But back to the ranking. So looking at the population density first, 84, 6.6, etc. Look down and identify your biggest number. That's going to be your ranking number 1. Followed by the second biggest, 2. This is the population density. 3, 4, 5, 6, 7, 8, 9, and we're going to take this one to 11, 10, and 11. Likewise, we're going to do it for the number of aggressive encounters. All right, 61 is going to be our largest one, and it's its own species. And so this might be more than just, being territorial, like they mentioned. They defend their territory. This might be more than just defending territory. If it's within their own species, the one thing that is going to indicate is maybe like a breeding, aggressive behavior for breeding. All right, that will be my 1. The next one is 2. No, it's not. This is 2. This is 3. 4. 5. 6. 7. Oh boy. There's a tie situation. So my next numbers should be 8 and then 9, but that can't be because they're both 3. So again, we take the average of those rankings. So 8 plus 9 divided by 2. All right, you're going to get 17 divided by 2, which is 8.5. So nobody gets to be 8, and no one has to be 9. 8.5. 8.5. And then my next ones, 10 and then 11. 2 and 2, same thing. So those should be 10 and 11, but they're both the same. So 10 plus 11 divided by 2, you have 21 divided by 2, and that's going to be 10.5. So nobody gets to be 10, and no one has to be 11 at the worst. We're at 10 and a half, and this one also becomes 10 and a half. Okay, I'm going to actually get rid of this for more space. And just for practice, we are going to do the difference, calculate the D, even though that doesn't have to be done for this exam question. It's actually done for you. But that might not be the case tomorrow. All right, remember D is the difference in the ranking. And then we need to do D squared. And we don't have to worry about, am I doing 5 minus 1 or 1 minus 5? It doesn't matter. Look for their absolute value, because then we're just going to square it. So this one's going to be 4, 1 minus 5, negative 4, but again, absolute value, it doesn't matter. 8 minus 7, 1. 11 minus 8.5 is 2.5. 4 minus 2 is 2. 10 minus 10.5, we have 0.5. 7 minus 3 is 4. 2 minus 1, 1. 6 minus 4, 2. 3 minus 8.5, 5.5. 5 minus 6 is going to be a difference of 1, and then 9 and then 10 and a half, difference of 1.5. You could do the negatives if you want, but it does not matter. And then I'll do one more table for D squared. just so that we're not getting confused with the numbers that we're looking at. These are the numbers that we're squaring. I know, because I'm starting to see like too many red numbers. All right, so what I just highlighted yellow is what we're squaring. D squared. So we have 16, 4 squared, 16. 1 squared is 1. 2.5 squared is 6.25. 2 squared is 4. 0.5 squared, so 0.5 times 0.5 is 0.25. 4 squared is 16. All right. And then the ugly one, the ugly part that we don't want to see, this one. I think that's the intimidating part of this equation. So we just did d squared, and now we need to do the sum of it. So just adding it all together. So 16, 1, 6, 6.25, 4.25, 16, 1, 4, 30.25, 1, and 2.5. Some of it is gonna be 82.05. And that actually will be a value that you will have needed to calculate in some later steps. But we have it now. And you saw how we got it again. So you have a couple of practices with this. All right, let's look at this data. One scientist suggests the following hypothesis. The greater the density of a species population, so the more there are per area, the greater the number of aggressive encounters with P. victoriae. This question doesn't ask you, but again, for practice, what if they did ask you to state a null hypothesis? Because I have seen that on like some paper 3s, which is A level, but you could still be asked that. The null hypothesis would state that there is no correlation between, and then we're going to insert the two things that they said. The density of a species population and the number of aggressive encounters from P. victoriae. The research data in table 4.1 were then analyzed. A scatter graph or a scatter plot using the data was plotted. Scatter graphs allow scientists to look for correlations between variables. So down here at your x-axis, you have the number of aggressive encounters. So those are increasing. And then at your y-axis, you have the amount of fish per area or population density. Something to notice, you have zeros at your axis. When you guys do a graph tomorrow, you can honestly just put 1 0. Okay, right away, there should be some things that kind of stand out. And that the one I'm talking about is right here. This is an outlier. This is something we wouldn't consider in the data, but it definitely lets us know that something not right happened. If you have to add in a line of best fit, they don't ask. You're going to bring in your ruler. Okay, and you want to try and get pretty even as you can. I always say like try and get half the data points above the ruler and then half the data points below. And not considering the outlier. So maybe it's something like this. But I mean, you can see that you got this one down here, though, this one down here, this one down here. What is going on right here? We have a pretty decent, at this line right here, you have comparatively a pretty decent density size. At that point, you have what, 27? Let's see, 20 to 30, so that's 10. You got 10 lines in between, so each box equals 1. So 30, 29, 28, 27. So you have 27 of fish per 500 square meters. And you have, same thing, 0 to 10. So you have 10, and then you are splitting it up by 10 boxes. Each box will equal 1. And so here, if I read it down, 1, 2, 3. So 27, and then I have 3 encounters, aggressive encounters. But then I got situations over here, and I'm only bringing this up because it's something you should be able to discuss. If I look all the way over here, 61, so 61 encounters, and my population is 30 and a half fish per square meter, per 500 meters. So 27 fish per 500 square meters, and I have 3 encounters. But I bring in 3.5 more fish, or about 4 more fish, and now I have 61. So 58 more encounters. That doesn't really fit. Look at your middle guys. So I got 29 aggressive encounters on this one, and my population is 8.5. On this one, 41 aggressive encounters, and my population is 26. It's not very strong data. It really isn't. It's not. And here, like, my population is higher than here I had what I say, 18. Here's 18 encounters, and the population is at 8.5 at this one. But then over here, I have 11 encounters, aggressive encounters. My population is almost 11 as well. But if my population decreases to 8.5, I have 18 number of aggressive encounters. There's a lot of holes in this data. So the scientists decided that a firm conclusion could not be drawn from the data. Use the data to explain this decision. I just did. Okay, so those are kind of things you want to talk about. And if you have data to support it, when it says use the data, use the data. Use data. Bring in examples. If you want to subtract and say, for example, when the population was insert number, there's, 17, 13, 10, whatever that number is, more aggressive encounters than when the population is. Use your data to support that. Okay, so in general, we could say the pattern is not clear, or something to that effect, or it's not consistent. There's an outlier, first of all, so it tells you something's wrong. At 84 per 500 meters squared, with only 12 aggressive encounters. And I'm abbreviating a lot, and of course we're not going to do that tomorrow either. And just like I said, we had some aggressive encounters occur with low populations. And I just showed you those. So like this one. At 8.5, we have, oh, this is the same one too. Essentially, yeah, 8.5, we have 29 encounters. That's the one I'm looking at. But with 27 up here, 27 per 500 square meters, there's only 3 encounters. So those don't really make sense. They don't fit. They don't make sense. They don't correlate. So you want to give an example with that? What did I say, 29 encounters? But with 27 per 500 square meters, there's 3 encounters, aggressive encounters. To analyze the data further, the scientists used the Spearman's rank correlation to decide if there was a correlation between the two variables, give reasons why they chose Spearman's rank correlation to analyze their data further. Well, they're certainly not measuring biodiversity, so they're not going to use Simpsons. They're not trying to assess the relative population size. They're not going to do mark and recapture, and they're not trying to do population size for things that don't move, so they're not going to use a quadrat, and they're not just looking for species distribution, so if there's a species present, so they're not going to use a line transect either. Oh, sorry, line transect is actually a sampling method. It's not even a formula, maybe. But the reason why is that this provides statistical, to be specific, analysis to test for data correlation. And then from the very first document I had, when data is not distributed in a numerical order. And that's the first thing that I actually showed you on the first document. Or we could also say this is to use a rank order of 2 variables or factors. Okay, and so they give us all of the data that we actually already just did, and then we're going to need to apply it to our formula. All right, and here's a perfect example of what they give you in a test. They give you the formula. They tell you what each variable means. Summation is the sum. Little n is the number of pairs between the items in the sample, so just essentially how many samples did you take? And then capital D is the difference in rank between your measurements. All right, and so they did the ranking for the population density size, and they did the ranking for the number of aggressive encounters. They calculated the difference, so did we. Those are the same values. And then they squared the differences. Okay, we can calculate for it now. Okay, so 6 times the summation of d squared all over n cubed minus n, 6 times, and the sum that we had, $82.05, or you would just go ahead and add all these together. 0.05? Yes. Divided by n cubed. We already calculated n. We did that on the very first data sheet. We said n is 11 because that's the amount of sets that they have. 11 cubed minus just regular n. Okay, 6 times 82.05. And I would do the calculator here, but actually the iPad doesn't have a calculator built in. What a flaw. If you do 6 times 82.05, you're going to get 492.3. And then 11 cubed is 1,331 minus 11. Let's move it down. And now we're doing 492.3, and 11331 minus 11 is 1320. And so this is the division you're doing now. If you divide that, you're going to get 0.37295, but you're not done yet. Because you need to do 1 minus that. There you go. So we're going to take this value and do 1 minus 0.37295. And just say, give your answer to 3 significant figures. So you will get, I'm just going to write the full answer out, and then we can identify the significant figures. 0.62705. And you need to answer to 3 significant figures. 6, 2, and 7. .627. This is 5 marks. And so the marks come from the following. 1 mark you would get if you were able to do the sum of d squared, right? That's 82.5. You would also get that instead of the same marking point, you have to get 82.5, and you have to identify that n is 11. So being able to identify n. The second marking point comes from you being able to show what you're dividing. So this part right here, 492.3 divided by 1,320 will give you the second mark. To be able to get the answer of 0.37295 of that division is the third mark. If you can take 1 and subtract it from that answer, that's the fourth marking point. And then to answer in correct significant figures, and they tell you 3, to have 0.627, specifically the 0.627, that's your fifth marking point. And so the last part of this is, what does your calculated value for RS, or the Spearman's rank, tell you about the original hypothesis? And if we need to go back, the original hypothesis is that the greater the density of a species population, the greater the number of aggressive encounters you have with P. victoriae. And like I mentioned in the document that I made, you could be given a P chart, or in this situation, you're not given a p-value, and you just need to know that if your critical value that you calculate is close to number 1, then we would say it's very has a high confidence. Sorry, there's a very high confidence that there is a correlation. This isn't that close. So we're at 0.625. So we're almost at like, I guess like 62, 63%. So it's not a ton of confidence. It's not a ton. There's a correlation, right? But it's not brilliant. So the answer can be accepted, or the calculated value can be accepted because it's closer to 1 than it is to 0. Okay, but this also shows a weak positive correlation. Last question, suggest what other factors, apart from the population density, so how many organisms there are, that could be affecting the number of aggressive encounters. So something other than, and not that something, for things to support this, other than they're just, defending their territory, which is what it said in the beginning of the first page of this. It says they're aggressively defending their territory from other fish. And things that we can use to suggest it is the data that we see on the very first page, and some things that I'm going to point out. So things that maybe you wouldn't know to look for, but now you do. Identify the top highest encounters, like what kind of organism that they're with. So 1 at 61, that's with their own species. Okay, and again, I mentioned in the beginning, this could be due to like breeding territory. But something that they tell us is their food source, so they're an herbivore. The second ranking has 41 encounters, also an herbivore. The third ranking, 29 encounters, also an herbivore. The fourth ranking, 18 encounters, also an herbivore. And your fifth ranking actually consumes zooplankton, so it's not eating plant material. So your top 4 aggressive encounters come from consuming herbivores. And then you have some omnivores in there that eat both. And I'm bringing that up to say that perhaps it's not just territory, and they're not being aggressive about their space, but it could be feeding competition or food sources. More encounters or aggressive encounters could be due to competition for food sources. And then, I have to have, it's a good thing to consider anyways. But I do have data to consider that, or to support that. For example, the top 4 highest aggressive encounters come from or are with herbivores, and its own species is also an herbivore. Back to my first thought, this could be due to breeding behavior or competition in their breeding game, competition and like the reproductive chances, like they're just competing for mates. And that's could be supported because the highest aggressive encounter is with their own species. Something else to consider, encounters could be due to territory size, right? So maybe if they're in a territory that's very large, they're not going to be, so territorial about their smaller areas, maybe something like that, or vice versa. Maybe encounters could be due to the number of nearby territories. Perhaps they have more to protect or they have less to protect. So now this one is like a very high value. And the quotes mean whatever I wrote above it, just bring it down. And then the mark scheme also mentions you could say an alternative valid point. And so just one that I could think of, and we do discuss it in A level, is the effect of like water pollution or runoff or coming from residential places. And one of the things that we do that ends up getting in our water is flushing down medicines or medicines getting released in our urine and then going through water treatment systems, but still being present when the water is released into like, rivers or our estuary. And one of those could be like contraceptives or birth control pills. Those have hormones in it, and that literally has a very high presence in a lot of our water. And those could also cause some hormonal imbalances between fish. Same thing with some detergents can do this. And side note, I read like within the past week, just I feel like a few days ago, but I'm so tired I don't remember the days. Just a few days ago, that one of the biggest medicinal products that are in the Indian River Lagoon are opiates because it's getting released through urine or flushed down the toilet. Like people are just throwing them away, or you can return them back safely. But that is that wasn't those things that's in there. But the alternative valid point, and the one that I thought of, was hormones in water or from wastewater runoff could be causing more aggressive behavior. And I wouldn't just say hormones in water causing more aggressive behavior. I wouldn't state that without saying maybe where it's coming from, but it's from wastewater runoff. Okay, that was the end of it. And good luck tomorrow. I think this might be the statistics that you're going to have to do. And if it is, I'll feel so validated that I did this. And for real, this is the last one for AS level. If you're taking A level next year, look out for me again. Good luck.